With its newest upgrade, Elon Musk has once again positioned the Cybercab as one of the most distinctive vehicles Tesla has ever developed. It is not only designed to be the company's most energy-efficient car, the least expensive to manufacture, and the vehicle with the fewest components, but it is also built specifically for Tesla's future Robotaxi network. Tesla has stated that the Cybercab will become the primary vehicle in its autonomous taxi fleet. By removing the steering wheel, pedals, and conventional driver controls, Tesla can create additional cabin space while also lowering weight, complexity, and operating expenses. At the same time, the company has introduced a major manufacturing innovation using reaction injection molding, or RIM, which could eliminate the traditional paint shop and reduce body panel production time from hours to only a few minutes. With more than 100 Cybercabs reportedly already assembled at Geiger, Texas, Tesla appears to be preparing for large-scale production. Yet despite these vehicles being built, not a single Cybercab has been delivered commercially. Large-scale deployment is still dependent on Tesla's full self-driving software, with FSD V15 expected sometime in late 2026 or early 2027. So the obvious question is, why is the Cybercab still waiting? By replacing conventional stamped steel body panels with lightweight reaction injection mold composite panels, Tesla could effectively remove two of the most expensive stages of traditional vehicle manufacturing: the paint shop and the massive stamping operation. Together, these facilities can require billions of dollars in investment and consume a huge portion of a conventional automotive factory's floor space. Tesla's RIM approach is designed to simplify this entire process. From an engineering standpoint, the RIM process combines two or more reactive liquid materials, commonly a polyol and an isocyanate, before injecting them into a low-pressure mold. The chemical reaction occurs inside the mold, allowing the material to cure rapidly and create a completed body panel within minutes. This replaces the conventional sequence of steel stamping, welding, corrosion protection, and painting with a much simpler manufacturing process. One of the most interesting parts of Tesla's approach is its in-mold pigmentation technology. Instead of producing the panel first and painting it afterward, UV-resistant color pigments can be mixed directly into the liquid composite material before injection. Once the molding cycle is finished, the panel comes out with its color and surface finish already integrated into the material. This eliminates the requirement for traditional paint booths and high-temperature curing ovens. The process could also reduce greenhouse gas emissions associated with these components by roughly 35%, while removing paint-related volatile organic compound emissions and potentially saving millions of gallons of water every year. When combined with Tesla's next-generation drivetrain, which is intended to reduce the use of rare earth materials, these manufacturing changes could create a completely different cost structure. By reducing expensive materials and simplifying the production process, Tesla is positioning the Cybercab for extremely high-volume manufacturing at significantly lower costs. That is essential if the company wants millions of inexpensive robo-taxis to become economically practical. But manufacturing the vehicle is only one part of the challenge. Tesla can build thousands of Cybercabs, but those vehicles still need to be legally approved and technically capable of operating without human drivers. That is where the biggest obstacle appears. At Geiger, Texas, more than 100 Cybercabs have reportedly already come off the production line. Yet commercial deliveries and large-scale deployment remain effectively at zero. The reason is straightforward but extremely important. The Cybercab was designed specifically as an SAE Level 4 autonomous robo-taxi, without a steering wheel, pedals, or traditional driver controls. Because of that design, Tesla cannot simply sell or deploy the vehicle at scale until it demonstrates that its full self-driving system can safely handle the required driving situations without human intervention. But how can Tesla sell a vehicle without a steering wheel to consumers when completely unsupervised autonomy remains a major legal and practical challenge? For now, it can't. Tesla appears to have made significant progress on the manufacturing side, but the company has encountered a much more difficult obstacle: the development and validation of its autonomous driving software. The gap becomes especially noticeable when looking at Tesla's existing robotaxi operations. A year after the highly publicized launch in Austin, the active fleet reportedly remains relatively small, with local officials estimating that only around 50 vehicles are operating. Even fewer of those vehicles have been running with completely unsupervised autonomy. Tesla has expanded its testing areas into places such as Dallas, Houston, and parts of Miami. But simply expanding the geographic testing map does not automatically eliminate the underlying software challenges. Elon Musk has acknowledged that the ultimate limiting factor is not necessarily production capacity, but the lengthy and demanding process of safety validation. As a result, Tesla's ambitious large-scale Cybercab deployment strategy remains dependent on future improvements to full self-driving, particularly the highly anticipated FSD V15. This delay highlights the central gamble behind Tesla's autonomous strategy. Tesla knows how to manufacture vehicles at enormous scale. But what happens when thousands of physical vehicles are ready while the software required to operate them safely is still being developed? Without a dependable software brain capable of handling complicated urban environments, without a safety driver, every newly produced Cybercab simply becomes another specialized vehicle waiting for its autonomous system to mature. If the software cannot reach the required level of reliability, the growing fleet becomes a massive investment in future AI capability rather than an active transportation network. The Cybercab also demonstrates the broader challenges facing the entire autonomous vehicle industry. Existing advanced driver assistance systems can still struggle with unpredictable weather, faded lane markings, connectivity problems, unusual road situations, and complicated questions surrounding legal responsibility. Removing the steering wheel entirely creates an even greater challenge, because regulators need a framework that determines who is responsible when a completely autonomous vehicle is involved in an incident. Compared with several Chinese autonomous driving competitors that use multiple expensive sensors, such as LiDAR, and operate within carefully controlled geofenced areas, Tesla is taking a very different approach. The company is making a major bet on camera-based perception, powerful neural networks, and software-driven autonomy. The key question is whether this vision-based strategy can ultimately handle the unpredictability of real-world traffic at the level required for true Level 4 autonomy. To close this enormous capability gap, Tesla is also working to provide the Cybercab with substantial onboard computing power. While much of the public attention has focused on the vehicle's unusual wheelless interior, its computing hardware may be one of its most important features. The Cybercab is expected to use a significantly more capable version of Tesla's full self-driving computer compared with the hardware found in standard consumer vehicles such as the Model 3 and Model Y. A major part of this upgrade appears to involve increasing onboard memory. Standard Tesla AI4 hardware is paired with 16 GB of RAM per chip. Since a typical FSD computer contains 2 chips, the combined capacity can reach approximately 32 GB. The Cybercab's computing platform appears to go beyond that level. Exactly which processor configuration is being used remains uncertain. Early production vehicles could potentially use an enhanced version of the AI4 platform, such as the AI4 Plus architecture discussed by Tesla, or a specialized configuration using multiple existing AI4 boards. There is also speculation about whether early hardware could contain elements related to Tesla's next-generation AI5 architecture, although AI5 has been associated with future production timelines. Regardless of the exact processor, giving the Cybercab additional computing and memory capacity would provide Tesla with more room to run increasingly sophisticated AI models in the future. That extra memory is extremely important because Tesla's full self-driving software is becoming increasingly dependent on large end-to-end neural networks. As these models become more complex, they require more computational resources and memory. Existing consumer vehicles can eventually encounter memory limitations, as Tesla continues expanding the size and complexity of its AI systems. By providing the Cybercab with significantly more memory, potentially reaching around 64 gigabytes if an AI4 Plus type configuration is used, Tesla could create additional computational headroom for future software generations. This would allow the vehicle to process larger AI models with less risk of memory-related limitations and potentially lower latency. Ultimately, however, the Cybercab will only become a true commercial product when Tesla proves that it can safely handle the legal, technical, and ethical responsibilities associated with driverless transportation. Building the hardware quickly is not enough. Until Tesla's autonomous software reaches the necessary reliability and receives the appropriate regulatory approval, the Cybercab cannot operate as the fully autonomous transportation platform it was designed to become. For now, it remains an extremely advanced vehicle waiting for its software capabilities to catch up with its hardware. But full self-driving is not the only reason the Cybercab is important. Tesla's latest impact-related reporting suggests that the vehicle has been designed around a completely different economic model from a traditional passenger car. Instead of treating the Cybercab as another consumer EV, Tesla is developing it as the foundation of a future autonomous transportation network. That means manufacturing cost, energy consumption, maintenance, operating efficiency, and vehicle utilization become far more important than traditional automotive performance. One of Tesla's most interesting targets is an efficiency figure of approximately 6.1 miles per kilowatt-hour, equivalent to around 165 watt-hours per mile. For comparison, the Model 3 long-range typically achieves roughly 4.0 to 4.5 miles per kilowatt-hour under real-world conditions. If Tesla can achieve its projected target, the Cybercab could deliver roughly 35 to 50% better energy efficiency. That difference becomes extremely important for a commercial robotaxi that could potentially operate for many hours every day. Much of this efficiency comes from the Cybercab's purpose-built design. By removing the steering wheel, pedals, and other traditional driver controls, Tesla can simplify the vehicle while reducing weight and mechanical complexity. EPA-related information has listed the Cybercab at approximately 3,113 pounds, which would make it significantly lighter than a Model 3, while still carrying dedicated autonomous computing hardware. A lighter vehicle requires less energy to move, while fewer mechanical components can also mean fewer potential failure points. That could translate into lower maintenance expenses and greater vehicle availability, both of which are extremely important for a profitable robotaxi network. Tesla is also combining this lightweight architecture with a newly developed permanent magnet motor and a reduced dependence on rare earth materials. Together with the simplified manufacturing process, these changes are intended to create a vehicle that is inexpensive to produce and extremely economical to operate. That could make large-scale autonomous taxi deployment financially attractive if Tesla can achieve its targeted production and efficiency numbers. The environmental benefits also extend beyond the manufacturing process. Tesla argues that a robotaxi could reduce lifetime greenhouse gas emissions because the vehicle would spend significantly more time carrying passengers rather than sitting unused in a parking space. Higher utilization means one EV can complete many more trips throughout its lifetime. When that higher utilization is combined with lower energy consumption per mile, total emissions could be reduced even in regions where electricity generation still depends partly on fossil fuels. By presenting these targets through its impact reporting, Tesla is communicating a broader message to investors, regulators, and potential fleet operators. The Cybercab is not simply intended to be another electric vehicle. It is being designed as a commercial transportation platform. However, one major question remains unanswered. Can the Cybercab actually maintain its projected efficiency of around 6.1 miles per kilowatt-hour under demanding real-world commercial conditions? Constant air conditioning, changing passenger loads, stop-and-go traffic, hills, weather conditions, and continuous urban operation could all affect actual efficiency. Alongside the readiness of full self-driving, the answer to that question will ultimately determine whether the Cybercab becomes the economic foundation of Tesla's future Robotaxi network, or remains an ambitious engineering project waiting for its final breakthrough. Thanks for watching. Make sure to hit the like button, subscribe to the channel, and turn on notifications so you don't miss our next breakdown. See you in the next video.